Okay, welcome to another episode of SYCL Sessions. My name is Rob Burns. I work at CodePlay. I'm a strong advocate for open standards for developers and in particular SYCL. And the company that I work for, we work on multiple SYCL implementations as well as chairing the SYCL standard working group, and we're also involved in helping to define some of that standard. And I'm joined again by Tom Deakin. Hi, Tom.
Hi, for those who don't know me, I'm Tom Deakin. I'm a lecturer in advanced computer systems at the University of Bristol in the UK. Also a member of the SYCL working group, and my main research focus is in performance portability, so how to get scientific applications running well on multiple different types of architecture.
Cool. So we have another guest joining us today, but I guess before then we can talk a bit about some of the things that have been happening since the last episode, well, in relation to SYCL. So I guess the main thing that has cropped up, which I think we've seen today, is the program for iWOCL and SYCLCon. So the program's now on the website, and looks like there's some interesting talks and papers on there. I think I did a quick count and there were 22 SYCL talks in the program this year, which after doing another quick count seems to compare to about 14 last year maybe. So it's quite a big increase in the number of talks, and I guess that's the benefit of an online format, is that there's a bit more room in the schedule to add in other talks, but it's really shows the variety of research that's going on and covers a lot of different range of topics. So Tom, you've been involved with the conference for a few years, I know, in helping Simon organise that and doing talks yourself. Have you spotted any sessions that are jumping out at you, or noticed any trends or things like that?
Yeah, definitely. I mean, iWOCL, as you say, has been going for a while. This is its 10th year. So this is the 10th year of iWOCL, and in the last few years, we've seen this very large growth in SYCL, and it's a very natural companion to talk about OpenCL and SYCL together at a workshop, given the history of those two. So that's one trend I've noticed over the years, is the balance of submissions relating to SYCL has definitely increased, and that's accelerated in the last few years. It's really great to be able to run iWOCL and SYCLCon together. And it's a really lovely event. We always get lots of great people attending, and it's always a mixture of people involved with the standards themselves, the people implementing those standards, and the users using those standards. So it's a real melting pot to get all of those conversations happening together. So it's a lovely event. Running it online as well hopefully means we can reach a few more people, and yeah, we can have the capacity to have the talks. I was on the program committee for iWOCL, as I have been for a few years, and a lot of the submissions this year were really fantastic. So we wanted to include as many of them as possible. So yeah, I'm really excited about iWOCL. So it's coming up in May. It'll be online. It's free registration as it's online, as we don't need to charge as we are a virtual conference. So yeah, if you're interested, please go to the website iwocl.org and register and attend the event. Is there any talks in particular that caught your eye?
Well, I'm always interested in seeing the performance studies, and there's a few of them that I've spotted in there. I haven't read through all the abstracts in detail, but some of those look quite interesting. I mean, you're talking about the variety. I know that even just from amongst my own colleagues, there's a talk on SYCL safety critical, which is a new a new specific forum to talk about how to make SYCL usable in a safety critical environment. But we also have a talk which is on how we've implemented some stuff in our own SYCL compiler in Compute CPP, and also talking about some work that we've done on host device. So yeah, so there's a lot of different topics, and in fact, actually, I think one of my other colleagues is presenting some algorithm work that they've done, and some performance results of that. So yeah, no, I think there's going to be a lot of different stuff to see there. It's going to be good.
Yeah, it's really good.
Um,
And to sort of kind of counteract all that implementation kind of talks, I noticed a few people trying to use SYCL for real in their scientific applications. So there's a talk from some folks at the University of Cambridge that have tried to add SYCL to their code and going to be presenting some results. An update on NAMD. It's a very very well known and popular code, and they've been trying to port parts of that to SYCL, and we'll be talking about that too. So it really does cover a wide range of topics at the conference. And don't forget, of course, the tutorial. So if you're new to SYCL and you want to learn a lot more, Rod here is going to be running a tutorial at the beginning of the conference. Have you got anything
to
say about that?
I think there's a couple of tutorials. So we're organising one which is going to be based on like fundamentals of SYCL programming and helping people to learn those things that can help them to get up and running. I think there's also another tutorial that's more specific to using the DP++ compiler and the Intel Dev Cloud and stuff like that as well. So yes, there's lots of opportunities to learn. Cool. Okay, well, let's move on, I guess, talk about some of the other things that have been happening. So I was involved recently in doing a SYCL sort of training workshop. So the company Codeplay that I work for, we're working in partnership with LBNL, which is the Lawrence Berkeley National Lab in the US, to enable SYCL for their pre-exascale Perlmutter supercomputer. So we are working to add latest features to support NVIDIA A100 GPUs, which is what is on the Perlmutter supercomputer. And recently, for example, we added some support for Tensor Core, which is quite specific for that architecture GPU. So we organised a workshop for Perlmutter users this month, in fact, March, that is, just to help them to understand how to get the most out of SYCL and how to use some more like CUDA specific features. So you can go back and watch it on YouTube. It's been published as a public thing by the NERSC group, which is good. So we can put a link to that in there, and you can take a look at that.
Yeah, that sounds really great.
Yeah, and I think the other thing that I spotted, which I guess is kind of relevant to our guest speaker today, was for part of the Google Summer of Code program, there's a proposal to add support for using the SYCL Alpaca backend to patatrack pixel track reconstruction. So Alpaca is an abstraction library that enables kernel execution, tries to abstract away some of the complexities of parallel execution on different backends. And there is a SYCL implementation for Alpaca backend. So they're planning on using that to enable some acceleration of that reconstruction experiment. So it'll be interesting to see how that goes through the summer. And, if that gets some traction within CERN and becomes part of the code that they use in production. So it's good link into our guest today. So our guest today is Attila Krasznahorkay, who's working as part of the Atlas experiment at CERN, which is part of the wider Large Hadron Collider project.
So these days I'm actually what we call the core software convener of the Atlas experiment. So I wanted to start with just a little bit of an overview of what everything that we do is about, because while I promised that I'll get to the actually interesting part and the actual code part at the end, I thought we just had to put at least a little bit of context around this. Otherwise, I imagine people will appreciate it a bit less, what we actually do. So just to start with the quote larger picture, I imagine that these days, especially because the during the last decade, we did some interesting stuff. People generally have heard about CERN, or at least they have heard about it a lot more than they did in decades past. But CERN by now has had a long history. It was created just after World War II by UNESCO, or in a large part by UNESCO. So this is just a fun fact that many people, I imagine, don't know, that CERN kind of sort of belongs to the UN. Even if technically that doesn't mean a whole lot these days. And it's basically a large collaboration between pretty much all of the European states, and these days not even just the European ones, but also since CERN became a worldwide organization, a number of non-European member states as well. Of course, what I imagine most people know about CERN is our current flagship project, the Large Hadron Collider. But while it is definitely the largest experiment that we are doing, and actually the largest physics experiment that mankind has ever done, it is not the only thing that CERN is doing. The institute actually has a number of accelerators. With a number of physics experiments being done on them. The LHC is sort of the final piece of the experiment of the accelerator chain at CERN. Now, the ATLAS experiment is then one of the experiments at the LHC. It's one of the two general purpose experiments, which in this case just means that, well, the experiment tries to do all kinds of physics. We have in total 4 experiments at the LHC. 2 of them are specifically designed for certain parts of physics, and the other 2 are general purpose ones. Now, usually the analogy that we like to mention in outreach settings is that you can think about the experiment, the detector itself, as a huge digital camera, because for all intents and purposes, that's sort of how it behaves. It's just that we have about 200 million channels that we can read out from the detector in all of 3D space, and we are able to, well, we are sort of able to read it out with 40 megahertz. Not really, but the hardware itself is capable of recording events at this speed. And I thought that just because we have a couple of these now outreach videos, just to give people at least a little bit of a sense of, okay, what are we actually doing? I wanted to play this this short animation that people put together already quite a while ago about, okay, what does the experiment actually do? People may have seen this because it's on YouTube. So the animation just shows that first of all, the LHC accelerates protons in it, and I just wanted to stop the video here for a moment to show that, well, the animation is even showing how protons themselves are pretty complicated things themselves. So even about the physics, one could talk for a long time here. But so what happens is that the protons are being accelerated, and then they are focused such that that protons coming from opposite direction would collide just in the very center of the detector, and this is where the actual physics happens that we want to measure. That when protons collide at such high energies, they can create new particles, and what the experiment is there to detect are all of these outflying particles. this is in principle the whole purpose of the detector, to detect all of these particles flying out, identify them, and just record what happened. In this particular case, the animation actually represents what happened in a real data event more than a decade ago, because, well, the LHC is getting on in its years by now, where an electron-positron pair would have been created. So so this is more or less what what these experiments are doing. Okay, maybe I can go on. But while today I wanted to mainly talk about one part of our software, how we interpret the data, how we reconstruct the data. This is really just one piece of the puzzle of what we do. There's a lot of software being used just to control the experiment, to record all of this data. Then there is a huge amount of software used to distribute this data over what we call the LHC worldwide grid, which consists of hundreds of thousands of CPUs and hundreds of petabytes of storage. And what you can see here is really just the storage currently used by Atlas, and not even counting all of the other LHC experiments. So just we ourselves use hundreds of petabytes of data, and our software needs to be able to handle this much data with a reasonable turnaround time. Now, as I said, most of what I want to show today is about how we interpret the data, because much like with the digital camera, after we read out the signals from the detectors themselves, we want to make some sense of what it was that produced those signals. Now, there is again a lot of physics behind all of this, that we designed the detector itself in such a way that different types of particles would leave different kinds of signals in it. And yeah, this is one of the drawings that we like to show about this. Vince showed this the last time as well. But without going into any of the details, it's really just meant to convey that the relatively known types of particles like electrons, protons, they would leave a pretty different tracks, different signatures in the detector. And this is what the reconstruction software is there to make use of. That the reconstruction software is meant to identify all of the what we call stable particles that reached the detector and then lost their energy in the detector. So what comes out is a list of electrons, protons, and whatnot with all of their properties. This is what it's meant to do. Now, very often when people just hear about this part of our data processing, they might get the idea that, well, okay, so this is what it means to analyze the data. But really, reconstruction is just what we do to understand what happens in an individual proton-proton collision. So in one particular collision, maybe a muon came out, as you can see here, without going into the details of why this is a muon and why anything is what it is. And then in a different event, you would see an electron-positron pair. Now, to actually get physics out of all of this, we have to run through billions of these events and do some sort of statistical analysis on how all of these events behaved. And that's how we actually get some physics out of it all, with just one pretty publicized picture from the last decade of how we convinced ourselves that the Higgs particle would indeed exist. So so there's a lot of software around here. I'm really just focusing on one part, but software-wise, this is one of the most complicated parts, at least. So then let me talk just a little bit about the software, because this is also something that that came up in Vince's presentation, and I heard that that you two were a bit taken aback by the size of our software, and indeed it's pretty significant. By now we have all of what we call our offline software in a single Git repository. And offline here really just means that this is the software that we use after we recorded the data to then understand that data. There are different kinds of software, but again, let's just focus on this one here. And just yesterday, I had another look at how many lines of code we actually have currently in the repository. It actually shrunk a little bit over the last few years because we threw out a whole lot of obsolete code. Especially we threw out a lot of Python code, as I had to find that by now we only have about 1 million lines of Python in there, but we still have about 4 million lines of C++. And what really makes things even more complicated is that this is not even all of our software. So these 4 million lines of C++ are just the software that we wrote specifically for Atlas. We use this software on top of a lot of other pieces of software that other people in high energy physics would have written. So this doesn't even include the hundreds of thousands of lines of code of simulation code that all of the experiments use, and so on. So just the size of our software can be pretty significant. And again, just to add to the ethos of all of this, I wanted to quickly flash that it's not just the amount of software and the amount of number of lines of code that we have that is significant, but yeah, just running it is a pretty significant endeavor, because we need a lot of computing power and a lot of memory to be able to run these things. Now, the reason that I wanted to point out the memory part is that just now we are starting the so-called run 3 of the LHC, during which we will, for the first time, use a multi-threaded reconstruction software. Up until now, we were able to get away with just making use of multiprocessing in our reconstruction through clever use of Linux's copy on write feature. But by now, you know, with CPUs becoming available with a lot of threads, in order to fit into the memory that we would get on these CPU resources, we had to make our software multi-threaded. And this also very much means that once we want to go to an accelerated setup, our software will still be multi-threaded. So whatever way we choose to offload accelerated calculations to some non-CPU device, we have to make it be friendly towards the multi-threading that we use underneath. Whether it will be still TBB at that point, we'll have to see. But threading building blocks has served high energy physics very well in the last decade. So we probably will not go away from it. And sort of the final piece of the background puzzle is that, as you see, we have a lot of software. We've wrote all of this software starting in the middle of the 90s, or you could argue that a lot of the algorithms were already developed starting in the 60s. So we have software in place that is able to do what we want. The problem that we face now is that many of those algorithms that we developed for understanding what happened in our detector are not behaving linearly. the complexity of these events. So in the high luminosity LHC means that a lot more complicated events will be created in the proton collisions with thousands or tens of thousands of particles flying out. And then our software has to individually identify tens of thousands of tracks. And our current software is just not behaving in a nice way as more and more tracks need to be reconstructed. So of course we need to do a lot of planning into what sort of hardware will we be buying in the long term, and whether we would fit into our budget in the long term. It's sort of its own thing how managing an experiment of this size is done, and we had to realize a good number of years ago that unless we did some what we call aggressive R&D in how to make our software faster, there would just be no way that we would fit into the budget that we had available, because with just the CPUs and the sort of code that we had up until then, we would not be able to process all the data that we wanted to take. So a number of years ago, well, by now quite a number of years ago, accelerators became pretty popular, and they may be our way out of all of this, because as you most people hopefully listening to this know, what the major way in which more and more compute power was added to high performance computers in the last decade or so was that they were filled up with GPUs and other kinds of accelerators, and this is definitely going to continue in years to come. Now, in order to make it possible for Atlas software to use these HPC centers, we have to be able to make use of all of their hardware. Plus, even our dedicated computing centers are now starting to buy GPUs because, well, again, a complicated situation. At the same time, things are still a bit fragile around GPUs, because in order for us to actually buy a large amount of accelerators for ourselves and not just make use of something that somebody bought for other purposes, we have to be able to demonstrate that it actually makes sense budget-wise to use these. So this is sort of in the current situation that we are in, that we are, and not just Atlas, but all of the LHC experiments are still in sort of this stage where we are trying to justify that we put all of this effort into making our code be able to run on accelerators. And this brings me to the actual R&D that we are heavily working on at the moment. Now, I showed you the Atlas repository before, which is our big software repository. Now, a number of years ago, part of the reconstruction was split off into its own project. So this is actually the most CPU expensive part of the reconstruction. This is where we try to find the helix tracks of charged particles. So the tracks of them are on a helix because we have a magnetic field in the detector. And this software has now been worked on for a few years to make it independent of the Atlas detector, and to finally make a piece of software that would be able to serve future experiments as well. Because so far, pretty much whenever a new experiment was built, software for it was sort of written from scratch. So you can find this project in GitHub. by now. It's not even in the CERN repository. And we will definitely make use of this software, the ACTS software, during the HiLumi LHC inside of Athena. But ACTS itself is really, at this point, primarily focusing on CPU execution. We are now trying to expand it to make use of GPUs. And what we did at that point is that instead of working with the ACTS repository, which already is a huge amount smaller than the Athena repository, we decided that, oh, well, we would go to even smaller projects for the R&D, and we just created some small repositories and small projects sort of from scratch, just to be able to freely play with ideas for the different aspects of track reconstruction. Because here we are really only focusing on reconstructing one particular type of object, just the charged particles. And all of these projects that I'll now try to go through them a little bit well, 3 of them are trying to solve different basic infrastructure issues that we need to be solved to run these things on a GPU. And the top one is supposed to bring everything together, as I'll show. So one of the first things that anybody who starts doing anything on GPUs will run into is how to manage memory. We did a number of different things for this in the past in R&D code pieces. But during the start of this R&D effort, we sort of by accident learned about C++17 memory resources. And since these were extremely close to what we were thinking of ourselves in the first place, because during the R&D, we started coming up with an idea that was pretty much the what was implemented as the C++ standard itself. So when we realized that, oh, okay, this is actually already part of the standard, we just ran with it. And this is what became the VecMem project, where we leave all of the memory allocations and deallocations up to what we call memory resource objects. And unfortunately, since I had a lot of nice examples just ready with CUDA in them, that those are the things that I copy pasted. But as you can see, in many of these base projects, you're actually experimenting with a number of different languages, because in the end, we are not trying to solve performance portability in this R&D. That's not the main purpose of this R&D. Instead, we are trying to write code which looks reasonably portable and reasonably maintainable, but at the same time, we are trying to demonstrate that we can actually write fast code like this. So okay, this is sort of the base idea of VecMem, that we leave all allocations and deallocations up to memory resources, and the complication that we put on top of this, and it is still pretty similar to what is in the C++ standard. It's just that nobody implemented it yet. Is that we also provide a bunch of higher level memory resources for caching, for the sort of interesting logic in memory allocations that we think will come in handy later on. Plus, one of the tricks that we do is that VecMem also provides like classes that mimic the STL containers in device code, because many of the existing libraries that we investigated for use, like Thrust and Cocos's own memory management. Most of those really just focus on what you do in host code. And in the device code, they just say that, well, okay, here is your pointer. Now do with it what you will. Instead, here we tried to provide people with STL-like container classes, both in host and device code. And well, you'll see in a moment what I mean by that. Now, I won't go into a lot of detail about all of the parts of what we do here. Again, I could easily be talking for hours about this, but one of the other interesting things that we do is that we want to be able to describe the exact geometry of the Atlas detector for some GPU code, which itself is a pretty difficult problem to solve, because all of the C++ code that we have written for it in the last few decades, well, let's say the last 2 decades, has been heavily based on C++'s object-oriented nature, and especially on polymorphism. And the latest version of the software that we use in our offline software in Athena to describe the Atlas geometry is fully polymorphic, and it decides at runtime what the exact type of a particular shape is. So the code that we use there is sort of polymorphism 101, that we define different shapes that are getting more and more concrete. Now, we can't really do that in device code, even though some people have started trying to make use of virtual functions in CUDA code, but of course that performs terribly. So we are trying to do some fancy stuff with our DETRAY project, where we don't do any we don't use any virtual functions or any polymorphism. Instead, we try to use what we started calling compile time polymorphism, where we would decide through variadic templating what sort of shapes we wanted to use in our geometry description. And once we made that decision through the declaration of the type, we would be able to just use the fixed types of containers and fixed number of containers in memory. And this is something that we are very heavily developing at the moment, and we are finally starting to see some results come out of it. And if you recall what I shown for VecMem earlier, we are basing the memory management of all of these higher level projects around VecMem. And we are trying to see how far we can take all of this by writing the detector class in such a way that it would be a relatively complicated template, which it has a number of other arguments as well. But one of the arguments that it takes is the type of vectors that it would use internally to handle containers, and allowing us to, in host code, build up the detector description and then transfer that description into device code and build up the same and make use of the same template, just with a different vector type inside of the device code. And so to avoid duplicating some of this code. So we are doing a little bit of portability here, but not quite to the level that Vince was describing. Now, there are other aspects that we need to solve as well. One of the more, I think, easily understandable problems is that we need to have access to the exact magnetic field in device code, which conceptually is a fairly simple problem. We need to save a 3D vector field in a 3D rectangle. So in a lot of places, we need to save the 3D vectors that describe the magnetic field. And then in device code, we need to be able to very quickly interpolate between the actual points in a fixed grid, where the grid might not even be equally spaced. And in that grid, we need to then interpolate very quickly from possibly thousands of threads while trying not to be cache limited. So this is something that we are actively looking at as well, how to make use of texture memory for these sort of things and how to lay out the memory to make things as optimal as possible. And then finally, where it all comes together, as I said, is the TrackCC prototype, where we are actually writing the algorithmic code that would reconstruct tracks. And yeah, because track reconstruction itself is a complex problem by itself. So here I was really just trying to flash a couple of drawings of what steps need to be taken to go from the raw readout of the detector to the helix parameters of the tracks that we found. And we are trying to attack this problem on a number of different fronts with writing code in different languages. And even inside of the different languages, we are trying out a couple of different implementations. So this drawing here is just demonstrating that for a particular step of the problem, we would have often multiple implementations. Yeah, the color coding is just trying to follow the industry color coding with team green and team blue. Yeah, as you can see, things are definitely not ready yet. Even we don't even have the CPU implementation ready for every single part. One of the things that we had a good understanding of how we would do it and how we would how we would handle this part of the issue is what we call the track seeding, which is a purely combinatorial problem. So this is one of the earlier parts of track finding, where we just need to find what we call a seed to our track, which in our case is a triplet of measurement points that look like they could be coming from a charged particle. So the algorithm here is just looking at all of the measurement points that we have in a given event and tries to find the triplets that look like they fit on a helix. This is where we already have at least some measurements of how our code behaves, both with CUDA and with DPCPP compiling code for an NVIDIA backend. Because in order to actually make performance measurements, we are even with Intel's compiler, we are practically always testing our code on NVIDIA hardware just to do relatively apples to apples comparisons. And so far, the SYCL compiler has been very good to us performance-wise. If anything, it might have generated a slightly faster code than native CUDA itself. At the same time, take all of these numbers with a huge grain of salt, because if you look back here of how we handle these different algorithms where we go from one data product to another data product, currently we are not focusing that much on hardcore optimizations just yet. At this point, we are trying to just make everything technically work. So for instance, we still copy more data back and forth between the host and the device than we think that eventually we will need to. So even in these speed up numbers, these are misleading for two reasons. One is that we are comparing the overall performance of a relatively beefy GPU to a single CPU thread. So of course, that's not realistic. At the same time, the GPU kernel itself is running even a whole lot faster than this. This time includes all of the memory copy back and forth between the host and the GPU. So while we don't actually have good performance numbers yet, we hope that that once we taught our code how to be more optimal with memory copies, that once all the algorithms run on the GPU, they would not have to copy back to the host, and we made our code multi-threaded, we hope that the speed up will still be good. But that's not a completely given thing at the moment. And yeah, just to flash some actual code, of course you can find all of these things in GitHub, and I believe we might be able to link the slides themselves to the video, because hopefully people will be able to, to have an actual look at this code if they are interested. Here I really just wanted to demonstrate that even for the relatively simple part of the problem, the seed finding, it's still a fair number of separate kernels and a fair number of steps that we do this in. And yeah, also just to show you how memory management is being done with the memory resources and everything. Now, as the final thing, I just wanted to quickly flash this. Unfortunately, this is one of the things that we are trying to figure out, but in my mind, this is going to be one of the things that makes or breaks all of this R&D, is whether we can make the final part of track reconstruction work in a reasonable way on a GPU, which is a Kalman filtering part. Where unfortunately Kalman filtering is just not a good fit for GPUs. That's just the fact of life. Nobody has really been able to crack this egg yet of how to run Kalman filtering on a lot of tracks at the same time. Because what we want to do is to run this sort of code on thousands, if not tens of thousands of tracks at the same time, keeping the GPU reasonably busy. Of course, if you just do a naive thing where you assign a single track to a single thread, technically that can work, but we actually saw in some previous R&D that, of course, performance is crap in such a case, because the different tracks just behave very differently. Your for loops become different sized. Yeah, GPUs don't like this. So we are thinking of a lot of ways of, okay, how to collaborate between the threads in fitting a single track, how to fit a number of tracks in a thread block in some smart way, so that the thread block can split up its own work for itself on a number of tracks. Unfortunately, we don't really have any answers at this point, or any results that, hey, this is how you're supposed to use it. So yeah, this is sort of where we are with this whole thing, that that we are really actively developing these R&D projects, sort of in isolation at the moment. But the goal is that by the end of this year, we want to take these out of R&D status. So the event, what we are developing for, as I've shown at the beginning, is the high luminosity LHC. So it's still a number of years off, where we have to be ready with all of this. But in order to have a chance of getting there, we have to decide by the end of this year how exactly we want to get there. So so this is what we are working actively on the moment. And if we convinced ourselves of how we want to get there, we will still have a lot of development and a tremendous amount of optimization ahead of us to actually do it. So thanks. Hopefully this was at least a little bit interesting.
Yeah, thanks, Attila. That's really interesting and quite fascinating to hear more about the projects and the experiments that are going on. Definitely. So yeah, thanks for joining us. If you're happy to stick around, we can ask you a few questions and have a chat about some of the things you've been talking about. Yes, I'm still a bit blown away by the kind of the scale of the software, and I suppose, as you say, it's kind of decades of development work that's gone into some of these experiments and simulations. It's
I was trying to find the application that we used a couple of years ago to assign a monetary value to our code, because I just couldn't remember the name of this thing anymore. But back then, that application told us that, yeah, in order to develop just the Athena code as an industrial thing would cost about $200 million.
Interesting. So, I suppose if you compare that to the cost of building the Large Hadron Collider, maybe it's not that much. I don't know.
It's not unrealistic because, of course, the way that all of this software was developed is that over decades, a lot of people who were paid by their institutes and by CERN to both build the detector and at the same time write the software, well, yeah, that added up to a lot of money being just paid out as the income of these people. So yes, this is sort of realistic. Right now, the developer count has gone down a little bit on Athena. Before the turn on of the experiment, so before the turn on of the LHC, but that was still before Git times, so it's a bit harder to get these numbers exactly. But back then, there were more than 1,000 people actively working on the software in parallel. These days, it's just like 100 or 200.
Okay, yeah, I was going to ask what the size of the teams are. That's interesting. Interesting to know. Yeah,
this is a really interesting point. Actually, there's a quote which I think is attributed to ECP, the US exascale computing project, although I can't find exactly who said it, but they came up with this idea that software was permanent and hardware is this temporary thing. So it was really interesting, your perspective on, how much human effort goes into maintaining these codes over the decades, but also how that's almost guided your approach as you need to increase your compute resource in the decisions that you're making of you need to solve your hard scientific challenges and make them not too unportable, but the science is coming first.
Things have changed with the LHC. So people like to tell these stories of how even at the beginning of the 2000s, people still had the mentality that, well, the software will just happen eventually, because in all the previous experiments, software was never the biggest issue. So people were trained to think that, well, we must sort out what the hardware is doing, what the detector is doing. Once we read out the detector, well, eventually we'll sort out the software. But the biggest problem with that is that previous experiments allowed us to record data relatively easily. The previous big experiment at CERN could get away with just selecting the interesting events in hardware, in simple hardware, that as long as there was enough energy deposited in the detector, we just recorded the event, and that was that. Now, even just to select which event we want to store for the rest of human history, or, well, however long things are persistent, we have to use a tremendous amount of software already. So it is, I believe, because of this that people realize that, and because the next round of experiments are not getting any simpler than the LHC, that, okay, now we have to change. And the ACTS code is fitting into this quite well, because this is one of the reasons that we separated track reconstruction into its own project, is that it would be able to be picked up by other experiments as well. And I know of 2 experiments that are being built which are looking at making use of ACTS.
Yeah, that's great. That's really cool.
Yeah, one thing I was going to ask about, you mentioned a worldwide grid, which I guess is a pool of resources or CPUs. Is that something that's sort of set up in different places, or are you using individual machines? I guess I was trying to get an idea of how the work is being distributed.
Yes, the worldwide LHC grid was something that people came up with at the end of the 90s and the beginning of the 2000s, since it was only at that time that x86 machines became really successful at CERN. And people decided that, well, okay, we can just buy a lot of x86 CPUs and use those to process the LHC data. And mind you, some of the first design reports that I've seen about this, they still projected that by the start of the LHC data taking, we would have 10 gigahertz CPUs, single core CPUs, and how we would scale to those things, because many of these extrapolations had to be done a decade in advance. But this part of the extrapolation sort of panned out that we could just buy a lot of regular PCs that we would connect up into large clusters of machines, and we would distribute the data processing on those. Now, these computing centers are a little bit different from what we call HPCs these days, because to me, HPCs are more things where we try to solve sort of one problem or one very well-defined issue using a lot of CPUs. The computing that we need ourselves is that we have all these billions of individual events that we recorded in the detector, and we can process those events completely separately from each other. So we have sort of a natural parallelization, just an embarrassing parallelism in what we do, and that's how we are able to use just hundreds of thousands of individual CPUs that we just tell them, you are processing these 100 events, you are processing those 100 events, and so on. Right, so yeah. the connection between all of these CPUs doesn't have to be super strong. We need strong networking between them just to distribute the events and then collect the reconstructed data out of them. But during the event processing, they just all do their individual things and then report back what they did. And so what ended up happening was that a whole system was designed in which countries could contribute to the LHC effort by buying their own hardware. So instead of paying CERN money so that CERN would buy hardware, all of these countries would buy their own hardware that they could also use for other things. So in most cases, these clusters are shared between the LHC and other scientific purposes. In many cases, they are shared between even like national interest computing and those sorts of things. And we just have a fair amount of software that we wrote that controls how we distribute compute power between these, how we can tell the system that, well, let's process this 10 petabytes of data, and where it would figure out, okay, where are the 10,000 or 100,000 files that we need to process for that? How do we split up the work? And it is exactly into this environment where we need to figure out how we will put GPU code into. Because just to scare you guys, we are in the last few months once again looking at how we could start making use of SSE 4.2 instructions in our code. Right now, when we build our code for x86, we do not use any even SSE optimizations, let alone AVX or anything more, because we have to run on even a decade-old hardware, and we have to be able to run on a lot of different things. And which very much ties into what Vince was also telling you the last time about that. We don't want to write code individually for one type of CPU, another type of CPU, one GPU, another GPU.
Yeah, it's an interesting problem to solve that, because I suppose if you have some algorithms that are designed to run on GPUs and some that are designed to run on CPUs, then I suppose if you have a chain of algorithms and some sort of simulation or processing, then you need to send it off to different machines to be processed.
Yeah, Vince also touched on this, that unfortunately, this is a big question mark. Okay, so there are multiple issues. First, I think, or at least I'm starting to think that we will not be able to write algorithms that just work well on both CPUs and GPUs. We've seen with the seed finding code that we have some amount of experience with already, that the code that we ended up writing, which would be optimal on a GPU, runs like crap on a CPU. So the comparisons that I made there, where I compared the performance of seed finding between the CPU and GPU, it's not the same code running on the CPU and the GPU. The CPU code is running CPU-specific code, while the GPU is running GPU-specific. What we hope for is that we would be able to just write one implementation of the GPU-specific algorithm, and at least not many of those. The other, what was I trying to validation. The thing is, our code right now, the actual production code that we use is not the most numerically stable, unfortunately. We absolutely know that when we run the same x86 executable on an AMD or an Intel chip, or just different generations of Intel's chips, we can get slightly different answers. Like, but to the level of, well, we might find a muon in the event, or we might not. Now, so far, we convinced ourselves that all of these objects appearing and disappearing, these are always very low quality objects. So objects that are, the software spits out that, well, it might be a muon, but in any analysis, you would throw them away because they are very low quality reconstructed objects. And this is what we hope with our GPU code as well, that it's impossible to make our results like binary equal at the end. They will not be bitwise equal, but hopefully at least statistically they will be equal enough that in any realistic analysis, when you are actually looking for physics, that there would be no difference between the two. But we will need to carefully convince ourselves that this is indeed the case. And yeah, unfortunately, I don't have the silver bullet yet. I'm not entirely sure how we will do that.
Yeah, that's an interesting problem to solve, definitely. Great. Okay, well, thanks again for joining us. That was a fascinating presentation, and it's such an incredible project for, I guess, everyone in the world, really. Yeah, privileged to have you on to talk about it. Hopefully we'll be able to talk to you again soon, maybe down the line when the project's moved forward even more.
Yeah, we should do that indeed. Hopefully we'll have during this year a lot of developments. So yeah, and thanks a lot for having me, and because we are trying to advertise this as well.
Yeah, no, it's good to be able to tell people a bit more about the stuff that you're doing. So thanks a lot.
Great. Thank you. That's really interesting.